advisor. So in that sense, we are like doctoral siblings. And she is member of the PHANGS collaboration, which she will tell us about today. She's visiting the Madrid, and particularly she's staying at the observatory until the 15th of December. And yeah, it is a pleasure to introduce her, and hope you will enjoy her talk.
Thank you for the nice introduction, and first of all, a big thank you to the organizers for letting me get the talk here at this lovely place in Madrid. It started raining today, but actually the weather is so much better than in Germany, so I'm really happy to be here. Yeah, and as Miguel said, I'm a PhD student from Heidelberg, Germany, and I'm here today to present you some of the work that I've been doing, which is about the morphologies of nearby galaxies from PHANGS based on a molecular gas distribution. But before I go into this in more detail, let me give you a brief overview of what this talk is going to be about, if that works. Okay. So morphologies can mean a lot of different things. So what I mean if I say morphologies are dynamical structures such as bars and spiral arms, which I'll spend most of the time talking about, but also about bar lanes, also often known as dust lanes. I'll explain them in more detail later. I also talk about gas flows due to these features. And last but not least, I'll talk a little bit about different types of rings that we can have in these galaxies. Okay. And to make it really clear exactly what I'm talking about, just one example how this can be done. So in our nearby universe, we have a galaxy all the structure with spiral arms, and a lot of galaxies have these elongated structures in the center, which are stellar bars. And roughly between half or even up to 2/3 of all galaxies in our universe are assumed to have these features. So they are relatively common. And we also see that these features correlate with other parameters in galaxies, an increased central gas concentration. We have peanut bulges, we have gas streaming motions due to these features, and generally also the ages of stellar populations on bars are older than the surrounding disk. So these features really have an impact on the evolution of galaxies. They're even assumed to be one of the main drivers of the secular evolution of galaxies in our universe. So we really want to know, of course, if we want to study any galaxy, if they have a bar or not. So let's say you found a new galaxy. Or maybe your supervisor assigned you a new galaxy and says, okay, please study this galaxy. And now you know, of course, how important it is to know if your galaxy has a bar or not. So you're asking yourself the question, does the galaxy have a bar? Well, this question can be answered quite simply. There's two things what you can do to get an answer to this question. First, you can try to look it up online. You can simply Google your galaxy and find out if there's any classification that tells you if this galaxy has a bar or not. And what usually pops up is something like this. Classifications like SA telling you it's an unbarred spiral galaxy, or SV, that there is this bar in this galaxy, which even goes back to the original Hubble sequence that Edwin Hubble started to classify. Back then it was still called nebulae on the sky, to classify if he sees certain structures or not. And some of these classifications are still used nowadays. Of course, they got expanded, so there's also intermediate bar types in some of the catalogs. And if you dig a little further, then there's also intermediate bars. And if you get confused by all these different classifications, and there's even more out there, there's of course a second option of what you can do. You can simply try to classify the galaxy yourself. And there's nothing wrong with that, because a lot of these catalogs out there are based on visual classifications. So astronomers looking at images of galaxies, classifying if they see a structure in there, if they see a bar or not. So you can do the same, of course. But then there's another question that you need to answer if you want to do that. What wavelength should you use? What image should you look at? Because, I mean, nowadays, for some galaxies, we have basically covered the full spectrum. We have observations from radio to X-ray data. And you potentially could use any of those? Does it matter at all? Well, in the literature, there's this idea out there that actually it depends. That some morphological structures are more easily visible in some wavelengths compared to others. Just to give you an example, for example, there's the so-called stronger bar effect. If you want to classify bars based on infrared data, they tend to be classified in slightly stronger categories than if you would use optical data of the same galaxies. And also, if you have a look at bar fractions from surveys using infrared data tend to be higher than bar fractions from surveys using optical data. And of course, there's a lot more playing a role here, like the survey selection, which type of galaxies are included. But one aspect might also be that bars are simply more easily visible in infrared data compared to optical data. So there might be a dependence between morphology and what wavelength you look at it. But most of these classifications in the literature are either infrared or optical, and both of that trace mostly the stellar distribution in galaxies. We know that our galaxies, there's not only stars in them, there's also a lot of dust and gas. So we were asking a question, why don't we use molecular gas distribution instead to classify whether we see bars or spiral arms or other structures? And I don't see really surprised faces or excited faces now. So let me actually rephrase this question. Why should we do that for those that are still not convinced? Well, there's two simple reasons for that. First of all, molecular gas is quite dissipated. So it sticks to the underlying gravitational potential really well. So we expect to see also changes in the potential. We expect to see them reflected in the molecular gas distribution. Generally, it's a really thin disk compared to the stellar distribution, which can be more expanding. And the second reason brings me to the so-called baryon life cycle. If we ever look at stars in our galaxies, they don't just come out of nowhere. It's actually a cycle where gas gets recycled over and over again. So in galaxies, we have atomic gas, diffuser gas, which at some, if the conditions are right, it can cool down, it can become denser and denser, form molecules, so we get dense molecular gas. And if it becomes even denser and denser, at one point it might collapse, and we might end up with nuclear fusion, and we have a star that's born. And these stars, they don't live forever. In their lifetime, they eject material back into the surrounding interstellar medium, and this material can be recycled again. Interestingly here, though, the phase that I'm looking at is the dense molecular gas phase. So it is the dense phase of the interstellar medium out of which stars in the future might be born. So we're looking at the material for future star formation. So looking at where this dense gas is might tell us something about where stars might form. So by trying to classify the morphologies of these galaxies based on a molecular gas distribution, we might be able to link directly the underlying gravitational potential with processes of star formation. So this was the motivation behind this work. And so we actually did this. We tried to classify the morphologies based solely on the molecular gas distribution. And to do that, we were using observations of carbon monoxide, second most common molecule in our universe. Most common molecule, molecular hydrogen, is a symmetric molecule, does not have a permanent dipole moment. It's pretty hard to observe. So the easiest way, what we can do is take the second most abundant molecule, carbon monoxide, rotational transition 2 to 1, observed with ALMA. And these observations, I'll tell you a little more about them in a second, because they are actually part of a collaboration, which is the so-called PHANGS collaboration. And I want to spend just a couple minutes talking about this collaboration, because we have actually a lot of people working on the data set that we have here. So PHANGS is not just galaxies, it's also people. Here just a couple of them from our team meeting in February this year. And there's a lot more also here in Madrid. So we have Miguel, we have Sophia, we have Enrico, we have Marina, and I hope I didn't forget anybody. So we have a lot of people from PHANGS working here in Madrid. So if you want to know more about what PHANGS is actually doing and the details, you can also ask them. Yeah, so this is the collaboration, and PHANGS actually stands for Physics at High Angular Resolution in Nearby Galaxies. So the goal is to study the physics of the galaxies at resolved scales. So we're not necessarily interested in how one single star forms, and also not maybe how out of one cloud several stars form, but rather to connect it on galactic scales. So to see how stars are formed, how they are impacted by dynamical structures such as spiral arms or bars, how this all is connected. And since one galaxy can always be an outlier, we're using about 100 galaxies, so a full sample of galaxies. And these galaxies are not just any type of galaxies, but they're actually carefully selected. So in our nearby universe, if we have a look at the star formation rate of galaxies as a function of the stellar mass, then we see that this is just a cartoon, but then we see that most galaxies actually clump together to form the so-called main sequence of star-forming galaxies. We have, of course, galaxies down here, red and black ellipticals, for example, where not that many stars are formed, and we have starbursts, galaxies in which a lot of stars are formed. But if we now want to study the star formation, typical star formation in typical galaxies, then we want to have galaxies that are on this main sequence. And that is also how they are selected. So here's now the actual plot showing the star formation rate and stellar mass. So in gray is data points from the Z0 MGS survey, so just typical galaxies, nearby galaxies. And in blue, the data points is the galaxies observed with ALMA in our FANGS sample, which is about 100 galaxies. And I'm quoting different numbers here because the number is increasing. So in my study, I'm using 90 galaxies, but actually I think the number is even above 100 by now. Because there's more and more data sets in the archive that we can use to refine and dig up. So yeah, please, apologies if I say different numbers from time to time. And some of the galaxies are also observed with different instruments. About 19 are observed with MUSE, about 39 with HST, and we also have the first James Webb images. It should be in the end also about 19, I think, that will be observed with James Webb. I think not all of the observations are complete yet, and some of the data reduction is still ongoing, but there also will be a lot more data to use. And all of these galaxies are nearby, so less than 30 megaparsec, so that we can actually resolve the structures well, resolve potentially also some larger molecular clouds in there, and they're close to face-on, so that we can also see the structures and, for example, see the difference between the arm and interarm region, that we can actually really see that how that correlates with molecular gas. Okay, so this is how the galaxies are selected. And just to give you a couple of examples how the data looks like. So one of the HST images, HST 628, nice galaxy with beautiful spiral arms. The same galaxy observed with MUSE, this is the H-alpha image. And of course, I guess most of you have seen a similar version of this plot at one point, HST 628, observed by the James Webb Telescope. This was one of the first galaxies that have been observed with the James Webb Telescope. Yeah, but there'll be more data to use in the future. And what I'm looking at, again, is the densest gas phase of the molecular gas. So carbon monoxide observed with the alpha gamma, large millimeter and submillimeter array. Okay, so this is the setup, basically what we want to do. So we have our sample, a sample of about 100 galaxies, with our data, observations by ALMA, carbon monoxide. What about the methods? So we want to classify morphological structures. And what we did is we just stick to a visual classification. I know it's 2023 and machine learning is on the rise, so we also considered the possibility of doing that. But this kind of classification has never been done on a molecular gas medium before, so there wouldn't be any training data to use, and we don't know what to expect. We don't even know if it's working at all. So we stick to a visual classification, but we had 10 people doing this classification to ensure that we are really tracing beautiful features and we have a good agreement, and not just one person that's at this. And we had a flowchart of different things that we went through to basically just say, okay, what are the features that we're looking at? What do we see? And I'm going to go through all of these, and I'm going to start, first of all, with one brief comment, because I get this asked a lot of times. There are some outlier in FANGS. So some galaxies that were selected, and later on we found out that the inclination is actually a lot higher or lower. So some galaxies turned out to be more or less edge-on. So we removed all of them, or galaxies where the detections are not really nice. So we made sure we're really using only this that we can nicely see. So, of course, we classified the largest features, which is bars and spiral arms. And since we don't really know what to expect from a clumpy molecular medium, we came up with 3 new classifications for the bars, because as you'll see later on, bars actually look quite different in the molecular medium. So A meaning it's unbarred, B meaning there's a thicker bar, the surrounding region is not really cleared out, and C meaning that either the surrounding region is really nicely cleared out of gas, or we have 2 lanes that connect with the center. For the spiral arms, we stick with the usual classification. So 2 arms, meaning grand design, multiple arms, flocculent segments, and in about 2 or 3 galaxies, which are sort of more or less early type galaxies, there's a small molecular disk in the center. So they look like UFOs. So they have a really completely smooth disk in the center, which is also really small. So we had to come up with this classification, but it's about 2 or 3 galaxies, so they're not that statistically significant. So what is the result? How do bars and spiral arms look like in a molecular medium? Well, you're already looking at one of the results, because this picture does not only show beautifully how the molecular gas looks like, but it actually encodes the results of our classification. So on the left side, you can see colored in purple whether the galaxies are classified as being barred, or in red if they're classified as being unbarred. And on the right side, the spiral arm classifications. So in red meaning flocculent, in yellow multi-arm, or in purple grand design. And of course, there's a lot of galaxies classified in gray. This is because, again, we had 10 people doing this classification, and we wanted to make sure that we're really only getting the features where all people agree. So we said that at least 6 or 7 people need to agree on a feature, otherwise we drop it from any further analysis, and those end up in this gray area. Okay, this already looks quite nice, but we can of course do a little more. These galaxies, as I said, are selected to be from the main sequence. So star formation rate is a function of stellar mass. So of course the first thing we want to do is check where are those bars and spiral arms in the main sequence. And we can see that the unbarred galaxies in purple are the lower stellar mass compared to the barred galaxies in green. This is in agreement with some studies in the literature, but there are also some studies that disagree with this statement. If we have a look at the spiral arms, we can see that the flocculent galaxies in blue are at a lower stellar mass compared to the grand design, the 2-arm spiral systems. Also in agreement with some literature studies. And now that we see that both spiral arms and bars correlate with stellar mass, it is quite unsurprising that most of our grand designs are also in galaxies that have a bar, and most of the flocculent systems are also without a bar. And I could only find a very old paper that found the same thing from 1982. But actually, this connection between these features is still up to discussion. I was on a conference in July in Granada, and at this conference we actually had a discussion whether there could be a connection or not. Could it be that it's triggered star formation, triggered spiral arm formation, that the presence of a stellar bar can trigger the formation of spiral arms or not? Or maybe it's just a coincidence. There was a study by the ESGAP in 2019 who looked at the pitched angles and couldn't find any connection with the presence of a bar. So this is still up to discussion. If any of you have any insight on that, feel free to talk to me. I'm happy to learn more about this. So for now, we don't really know what's going on here. Potentially there is some connection, potentially not. But we also have to admit that the PHANGS sample is maybe not the most suitable to answer this question. Because in the end, we're still talking about roughly 90 galaxies, and in the literature, there are samples with many more galaxies in them. And all of these galaxies are nearby, so they have been mostly studied in the literature as well. So what we should do is, of course, compare our classifications with those from the literature, which are mostly based on the stellar distribution. That's exactly what we're going to do next. We do a literature comparison. So what we compare our classifications with classifications from the literature from UTA 2015, which is infrared data, or if not available, the Vokuler 1991, which is optical data. So we're comparing our molecular gas-based classifications with classifications from the stellar distribution. And the confusion matrix looks a little messy, but let me get into that in more detail. Let's start with the spiral arms. This one is easier. Let's start with them. So generally on the diagonal, there is sort of, it's a little darker, so there is some agreement here, but we also don't expect it to be perfect. I mean, here, the flocculent part seems quite nice, but we can especially spot that the multi-arm part did not work too well. So what is going on here? Well, we have to look at the reasons for that. So multi-arms are generally known to have a reduced arm-inter-arm contrast or tighter pitch angles, which might make it harder to see these features in molecular gas because it is really clumpy. Also, they have a smaller arm width compared to grand designs. Smaller arm width could mean that there's less gas that can accumulate on the arms, and again, make it hard to see it in molecular gas. On the other hand, molecular gas responds to the underlying features. So if in a multi-arm system there's 2 arms that are stronger, it could also be that, therefore, because the molecular gas responds to these then better, that we see these 2 arms, especially in the molecular medium. We don't know exactly what's going on here, but that would be some of the explanations what's going on here. But multi-arms are a little special anyway. In In most cases, we detected that there is a bar at all, which is what we basically hoped for. So we didn't expect perfect agreement. For most galaxies, it turned out to be quite well. However, there's 4 galaxies where apparently literature says it's a grand design spiral arm. So 2 beautiful spiral arms, which we didn't see at all in our survey. So we looked into this in more detail. We looked at where are these galaxies in our main sequence plot, not really anywhere special. So we had a look at the images, how do these galaxies look like? And just giving you 2 of these examples of these 4 galaxies, you can see what's the problem here. It's a field of view. This is one of the major disadvantages of the molecular medium. The spiral arms that are in these images are very likely just outside of our field of view, and we cannot really see these features. And this is sort of by design of the survey, because molecular gas is mostly confined in the central parts of galaxies, so the field of view is also constrained to only record the central parts of galaxy. Observation time is expensive, and also we don't expect to see much molecular gas further out. But if you ever want to do any similar study of this kind, be aware in the outer regions when the spiral arms are really far out, you will not be able to see them. Okay, going from the spiral arms back to the bars, this one looks a little more messy. But we have to admit that we're not comparing equal classifications here. So we have this ABC, this weird kind of classification system, which is not directly comparable to the SAB, SA_B, SB classification system. Generally, there is sort of some trend here, but again, we have a couple of outliers which are pretty extreme, which I'm not going to talk about next. So for example, we have 6 galaxies where the literature says there is strong evidence for a bar, which we don't see in our molecular medium. So we have a look at these galaxies. And if we look where they are in the main sequence, they're all at the lower stellar mass end. And if you remember earlier, I said that we see this beautiful trend with stellar mass, that the barred galaxies are all at the upper end here. Well, if these galaxies would be barred, this trend would not look so nice anymore. So these 6 galaxies are actually a problem for us. So we also had a closer look into them. And here's just one example, NGC 1559. So here in the top left, it's the Messier observations. Bottom left, 3.6 micron is what was used for the literature classifications, which are also for comparison. And here in the 3.6 micron, there is some elongated feature here. Oh, we don't see it in the molecular gas. We don't see it at all. There's no evidence for a bar in the molecular gas medium. And the other galaxies are similar. Some are more ambiguous, some less. But in all these cases, it is not really sure what's going on. It could be that maybe it's a gasless bar. Maybe it's a bar where there's just no gas accumulating on it. Maybe there's stuff when it comes to mimic elongated structures, so there is no actual bar. We cannot say for sure. But what we know is that the bars at the lower stellar mass end of our sample, they are really ambiguous. And what we also learn is that bars at the lower stellar mass end, if they are bars, they look completely different. So what we usually do is when we have a look at surveys that cover a large range of stellar masses, we expect the bars to all look the same, but they don't look all the same. So we really need to be careful if we have a look at bars in lower stellar masses. They behave differently, they look differently, maybe they aren't even bars. We don't know for sure, but certainly we need to be careful about that. And just to emphasize this even more, we can calculate the bar fraction based on our classifications. Of course, about 90 galaxies is not really that large of a sample number to constrain an actual bar fraction. But if we do that, we find about 45% bar fraction based on our molecular gas classifications, which is very similar to what optical surveys find in a sample of similar galaxies. If we now take the same galaxies and calculate the bar fraction based on the literature, this ends up with a fraction of 73%. So just to emphasize, of course, this is the 6 galaxies going in here, but also a couple more that are classified as SAB, SA_B, which I didn't show here. But these galaxies can really make a difference here in our little example here. So we really want to get these classifications right, and what we probably should do for the future is also have a look at the kinematics. So be careful with galaxies at lower stellar masses, because the bars may not be bars in them. Okay, one last example that I want to show now, more a positive example, is one galaxy where the literature did not find a bar, but we found a bar. So it's the opposite case. We're not missing bars, we found an additional bar. And this galaxy is NGC 4941. Again, the same images. And if you're not used to looking at bars in molecular medium, this probably doesn't look too special to you. Actually, really hard to see on the screen though. If you're used to looking at bars in a molecular medium over and over again, as I've done, then you immediately spot that there's two lanes that connect with the center. A little easier to see, of course, in the laptop. Which you simply cannot see in the other images because the center is also super bright. And these lanes are actually a clear sign of a bar. This is what we expect the bar to look like in molecular gas, to have these two lanes that connect with the center. And also in the literature, there's some inconclusive classification. So other classifications classify that there is a bar, whereas the one that we were using for this comparison said there is no bar. So it is not that clear for this galaxy. But with the molecular gas, we can say for sure that there is a stellar bar. And this is one of the major advantages of the molecular bar lengths. What are bar lengths? Let me talk about these bar lengths now as the second part of this talk. So if we have a look at a bar, the stellar orbits give us these nice orbits here, x1 orbits along the bar more or less. Center we can have these perpendicular orbits, x2 orbits. But the gas actually behaves a little different. The gas can get shocked and then funneled to the center along these orbits. And therefore, a bar in a molecular gas is not just an elongated feature, but actually we expect to see these two lanes that connect potentially with the ring in the center. But even just giving you these two examples, it becomes clear that they also don't all look the same. This is the theoretical example what we might expect to see. But of course, in reality, things are a little different here. So we of course also classified this. We went and had a look at the different bar lengths that we see in our sample, and we classified the length of them, meaning how much molecular gas we see. Does the structure connect with outer features? Or is there actually a hole in between and it doesn't reach out to any other structure? So we classify this as short or long. And we also compared these bar lengths with simulations from Astronomie 1992 to see what the curvature of these features is, if they're more curved or rather straight. And in addition to that, we also went to polar coordinates, so radius as a function of angle. We had a look at these bar length features. We masked out everything else like spiral arms or centers, and what remains is like an exponential function, which is these bar lengths, which we then also try to measure the length of. And by doing that, we end up with this plot here. On the x-axis is the measurement, whether these bar lengths are measured as whether short or long, colored by the visual classification of short or long in orange and in blue and orange. And on the y-axis is the curvature, whether they were straight or curved. And it's not a super duper clear plot, but what we see first of all is the visual classification agrees with our measurements. The blue points, especially the darker ones, which is the ones that we trust more because more people agreed on that feature, they are more to the left and the orange points are a little more to the right. And generally, it looks like there's two clumps in here. So we have up here and down here, which basically tells us that bar lengths that are shorter tend to be more curved. And bar lengths that are longer in the molecular gas tend to be straighter. And we also checked for other correlations, and we found that this is also correlated with the global molecular gas mass fraction. So the more molecular gas that is globally available, and we only found a very, very weak correlation here. So it's more like of data points. But of course, we're also only looking at less than 20 galaxies here. So the statistic is also not in our favor. And this was a similar thing was also found by Kommer in 2009. So lack of data points in one of the corners. So there might be a tentative trend with bar length here, but we should confirm this in the future, maybe with a larger sample set. But if we get a better statistic on this, we might be able to make constraints about global parameters of galaxies, or even the bar strength of a galaxy, by simply having a look at the geometry. That would be, of course, ideal, but again, we're a little bit lacking a better statistic here. So potentially in the future, with the James Webb measurements, where we see the dust lanes, we might be able to get better constraints. Okay, with that, I want to come to the third part of this talk. Now, looking at all these bar lanes, what we see is gas on these lanes that is transported to the center. Gas that is funneled to the center.
So of course we also want to ask the question how much gas is actually moving to the center, how much gas is funneling there. And this is a work that was done by Matthias Somani, Ashley, Jai, and me. And we actually tried to isolate these Barland features, try to measure them, how much gas is on them. And the result is an inflow rate of about 3 solar masses per year, which is nice. Can we put it into perspective? Well, yes, we can, because we can try to find out if the mass budget adds up. We have gas flowing inwards along these bar lanes, gas that funnels to the center. We have gas that is consumed by global star formation, so it gets removed from this equation, which is about 2 solar masses per year. And we also have gas that is being pushed outwards again, outflows. And the so-called outflow rate is about 7.6. So in this case, also giving you large uncertainties, the values add up nicely, but of course, the goal is to expand this to more galaxies, which Marina will have a look into in the future, to really find out if this mass budget also works for other galaxies. In this one galaxy, NGC 1097, it works out nicely. Now, talking about these outflows, how do we even know that galaxies have outflows? Do all galaxies have outflows? Or not? And if not, what kind of galaxies actually have outflows from the centers? And going then back to what we just learned about, how much gas is outflowing out of the centers? Can we compare it with inflow rates? And well, this is another study that I did in 2021, so I want to briefly talk about it. First of all, what is an outflow? An outflow is a relatively small amount of mass moving at relatively high velocities. So we're looking for broad rings in a spectrum, or if we take a precision velocity diagram, we expect sort of S-shaped rotation curve. We're looking for something suspicious on top of that. And we can also take these broad rings and integrate over them. Look, where is this emission actually coming from in a map of the galaxy? And we did this also for the full PHANGS sample. And we found that about 25% of the PHANGS galaxies show evidence for outflows in their centers. And we also did more. We tried to estimate then what is the actually outflowing rate, the masses of these outflows, the outflow rate. So here you can see the outflow rate, solar masses per year compared to the global star formation. And then that is our measured data point, so these 25%. And in blue is points from the literature from mainly starburst galaxies. We can see that our relatively typical, boring in a way, main sequence galaxies from PHANGS, they have outflows that are very much comparable with those from the literatures. They expand to this lower regime. So it's not really that these galaxies, there's nothing happening, and these starbursts, there's all this star formation happening in these extreme conditions. All that happens in main sequence galaxies as well, just on a little smaller scales. Yes, and of course we were also asking the question, what kind of galaxies have outflows? Because of course 25% means not all of our galaxies have outflows. So we were having a look at the AGN fraction, because that is one of the main mechanisms that could drive an outflow. Well, only about half of these outflow candidates have an AGN, which is still more than we have in the full sample, including these galaxies here. But so half of the galaxies do not have an AGN. But there's also another driving mechanism, which could be just starbursts in the center of the galaxy. And what we also checked is for the bar fractions. We can see that nearly all of these outflow candidates have a bar, which is also more than a PHANGS sample. But all these outflow candidates are also at higher stellar masses. So it could be just a coincidence that both these outflow features, they are maybe larger, they are maybe more massive at higher stellar masses, so we're able to detect them. And stellar bars are also more coincidentally more prevalent at higher stellar masses. Potentially, there's also a connection. Potentially, the bars are actually necessary to, first of all, funnel enough gas to the center so that the central starburst stream can build up. So we have some energy source that can drive the outflow. And of course, we need gas in the center to have an outflow. Without gas, there cannot be an outflow. So we don't know for sure, but this is one of the reasons that could happen why we see such a high bar fraction here. And this again tells us why it is so important to get the classifications of bars right, because they correlate with so many things. They also correlate with the outflowing gas. Okay, talking about the gas reservoir in the center, this is the last point that I want to talk about. asking a question, okay, you have this gas being removed from the center, funneling to the center. What has happened in the center? Well, in some cases, the gas can accumulate on these X2 orbits, and we can have rings form. So here's a couple of examples of rings, because rings can happen on different scales. The rings that I was just introducing, the rings in the centers of galaxies, two top examples. But of course, rings can also happen in the outer skirts of galaxies, outside of a bar, outside of spiral arms even. So we were classifying whether we see these kind of rings. So whether we see central rings, literature often referred to as nuclear rings, in case we get confused. And we called it non-central rings, so all kind of rings that is outside of a bar, for example. And for these non-central rings, I can make it a little quick. It's about 8% that we find. The problem is, again, that our field of view potentially is not large enough, so we're not really sure if we're missing some of these rings or not. We find that they're mostly in barred galaxies, which is in agreement with some studies, but also not with all. But again, our field of view might be one of the reasons why we're not detecting some of these rings, so this is not entirely sure. However, if we have a look at these central rings, also known as inner rings, you can see that, well, not always it's a perfect ring, sometimes it's a little elongated, but these features mainly exist due to the funneling of gas inside bars and the orbits that can be accumulated by gas. So about 30% of our galaxies have these rings, and most of them are in galaxies that are also barred. Also nicely in agreement with some literature studies. And to look into this even further, a bachelor student from me, Damian Gleis, actually currently tries to quantify the amount of gas that is in these rings. So by isolating these ring structures and trying to measure what is the amount of molecular gas that is in there. And so far, but it's still preliminary, we find that there's about 6% is diffraction of molecular gas in the ring compared to the full galaxy, which is pretty comparable to what we find in the Milky Way. So maybe this is just the same in all other galaxies here. But again, this is preliminary, so he's probably right now sitting at his computer trying to figure out the numbers. Okay, with that, I want to come to a brief future outlook, talking about JWST, because there's the first images that we have, more data still incoming. And of course, rings and bar lanes are really nicely visible in here as well. What we see with the JWST image, mostly the dust structures. Dust is able to shield molecular gas from being destroyed by radiation of stars. So some of the features seem to show us very similar structures than what we see in the molecular gas. So these bar lanes, you might be able to see them here as well, and might be able to classify them as well. So this is one of the future things that we might want to have a look into in more detail. And with that, I hope I could convince you that the molecular gas is actually able to trace molecular features quite well. We don't have a perfect agreement, but we didn't expect it because there are some physical reasons why this might be the case. And especially the lower stellar mass end of our galaxies, be careful with bars. They might not actually be bars. Maybe they are, and they're just behaving completely different. Still something to find out. We also could see that bar lanes is one of the nice things that we can see in the molecular gas distribution. We can try to do a lot of studies here. And we saw that both central rings and galactic outflows are preferentially in galaxies with a bar. So we really need to get this classification right. And in case you're using YouTube, I just want to advertise, we started a YouTube channel, it's called PHANGS team. There's currently about 3 videos in there, so we just started. But one of the videos is actually a shorter version of this talk. So if you feel like you want to hear it again, you can check it out. Thank you very much. Thank you.
Yeah, we have already questions. Why we have this correlation with flowers and how the bars going to understand.
Yeah, so it's just to basically build up a gas reservoir in the center. So I don't think the bar necessarily has any dynamical impact on that, so I mean, this is still up to study. So this is what my better student also looks into. But generally in the centers, I mean, there's these rings that we see there, they're really starbursty. So a lot of star formation happening. This could be one of the mechanisms to drive the outflows, the energy source. Because if we don't have an AGN, we need a different energy source to drive these outflows. So that could be one of the reasons that because of the bars, we get so much gas in the center that these starbursts can build up in the ring. And the second reason is that we just need enough gas in the center. So in some galaxies, if there's just no gas in the center, there's nothing we can push out. Even if there's an energy source, we have nothing that we can see here. So we need enough gas that gets pushed out again. So that was the argument here. Of course, we haven't done any calculations on this. So this is just the idea that could theoretically work out. Does it make sense?
So can you check, for instance, neutron gas to see that we have like a higher rate?
No, we don't have any full sample observations, I think, of neutral gas, as far as I'm aware. So the only one that we have is, so there's currently also a master student looking at the ionized gas, because alpha should be even easier to detect than ionized gas, but he's also on it right now, so he hasn't done that. Also, these 100 galaxies are only observed with ALMA, so we don't have any other observations, as far as I'm aware of, any other observations that cover all these 100 galaxies. So that's sort of a limit here. But it's, of course, something to check. So yeah, ionized gas is checked by master student Justus Neumann right now. Other gas phases not. Yeah.
But it's one observation on the way. So
yeah, that's true. Yes.
More questions? Yeah. Maris again.
Sorry, I was just wondering because I can see that your lowest mass limit is around 29.5.
Yes.
So do you have any plans to extend the sample to lower mass, for instance?
That is a very good question.
With Muse, yeah, for sure, and
Yeah.
in ALMA as well. Yeah, I think people listening to this.
Yeah.
It's already happening.
So there's really a lack of low mass galaxies.
Yeah, it's true.
Yeah.
Yeah, you're right.
Yeah. So if I say low mass, I mean this is not dwarf galaxies, but 10 to the 9 or something. So of course not. You can go lower. Yes, certainly. Yeah.
For this galaxy that you showed, where you saw a bar in the optical, was it?
Yeah.
The speed, you do see it in molecular gas. Could it be that you are missing some diffuse emission in ALMA that could be?
This one.
That,
Yes.
I think that one, yes.
Yeah. Yeah.
Could it be that you are losing some of the diffuse emission that you filter out when you're using the interferometer? That would maybe lead to some resentment of the structure?
That's a good question. So my takeaway is that for the bars, higher.
Can you repeat the question for the people that are online?
Sorry,
That otherwise
yes.
cannot.
Okay.
Sorry.
Yes, the question is if we if due to interferometers we're missing some diffuse emission that might help us to that we would see bars that are otherwise that right now we don't see in the data. So my take for this would be that so at higher stellar masses, of course, the bars might be different, but the bars generally, these two bar lanes that we see, a higher resolution would be better to see them. So not necessarily the diffuse component that's missing, but I don't know.
We have total power.
Yes, and we have total power. Yeah. I mean, we don't cover the full range, but so they are all with short spacing corrected. So we're adding total power to that. But still, I think it's not necessarily this. The bars wouldn't be like a broad structure or something. So the high resolution is actually better to detect them, I think. If that okay.
Is there any question from the audience online? If you have a question, just open your mic and speak up. Okay. Any other question here?
I have a question.
Yes.
You show in a few slides later the difference between the size of the bar, which the small one and the larger one. Do you think it could be in a hint of the evolutionary phase of the galaxy? You can say maybe a younger or older phase of the galaxy.
That potentially.
Correlation.
Yes, yeah. Potentially, this is an evolutionary theme. So one thing that would be really good is also to get the ages of the bars, but this is a really hard thing to constrain. So I think Justus Neumann is currently looking into this. If we can get some, I think there was some papers recently about how to estimate the ages of the bars, because I mean that would really help to find out is this actually the bar becoming older over time, and all the gas gets funneled so that and maybe there's no more gas coming inwards. So this is an older case, basically an evolutionary case. But I think we're lacking a little bit the age constraint on that. So
any good methods on age determination in bars, feel free to tell me.
Yeah, Dos Santos, bueno, Freitas Dos Santos, that when the bar formed, no,
Yeah,
you have
yeah.
like an increase in the star formation, like an
Yeah,
part
yeah,
in the star formation history. So she can constrain the epoch of bar formation by looking at the star formation history of the disk compared with that of the of the bar, and you will spread and determine. Yeah, well, see, it makes constraints on the edge of the bar reales, not the edge of the star. So. But yeah, I mean, it has its alternatives, but it's at least it's getting like a consistent result. And yeah, sorry. Sorry, who did? Someone there. Yeah. Annalise. Yeah, Annalise, you can ask a question if you want.
Hi, Sophia. Very nice talk. I have a question concerning the bar morphologies that you find. You said that you find some short bars in radius, but do you find any evidence for nested bars, like embedded bars, like as the model proposed by Schlossmann in, I think, 98, something like that, of this set of nested bars, so the bars within bars?
Yeah, thanks for the question. This is really nice. Let me think about it. So, I think there's a couple of cases, but do we have them in our side? Yes, we have some, right? Yeah. So I didn't look into that in much more detail, but that's definitely something good to do. Two cases, yeah. And we have the ALMA observation. Yeah, I should look into that in more detail. So we haven't done this yet, but this is something I should probably check. Yes.
Okay, thanks. And if I can ask another question quickly. Okay. You said that you find these inner rings as well, like in CO. Do you have any further evidence of structures inside the ring? Because we have some observations, but it's a much smaller sample of the Nuga galaxies. And for some of them, we found evidence of nuclear spires that are inside the inner ring. So I wonder if you also see this for some of the galaxies in the FANGS sample.
So I'm pretty certain that some of the galaxies have that. The problem is that our ALMA observations have about 100 parsec resolution, and these rings are just a couple of 100 parsec in size. So I think Nuga has a lot higher resolution observation. So for the molecular gas phase, we're certainly lacking the resolution here. I'm not too sure about the James Webb. I think there's already something going on to find. Yeah, people are staring at the James Webb images right now. So we would be able to see them here. I think, did somebody start looking into this? Marina will look into this. Yes. Yeah. So, but with the ALMA observations, 100 parsec, I think, is not enough to resolve these features, unfortunately.
Okay. Thanks.
Okay, I have a suggestion for the relation between the bars and the grand design paradigm. And it was the theory of the manifolds by people in Barcelona, by Mercedes. And I mean, in her theory, grand designs need bars. So it's right also because there are manifolds that come from bars. So there will be a clear connection, and in fact, you can actually falsify her theory if you find like grand designs that can come from a bar. So that will be a way to explain the
Yeah, I think I just remembered that I also read some papers that really nicely explain how you could form a bar, could form spiral arms with a bar. But I think some of the simulation side, they see that there's not necessarily a correct connection. But I'm also not too good with the literature.
Maybe now they say, well, I don't say. I think the bar manifolds they need a bar, but But I mean, no, you think so on, Or an interaction as well. That should make it as well. Exactly. Yeah. That also should make it. That would also make it.
But I think is it proven?
Well, it's a theory, but not the density wave theory is not proven either. So it's a theory to explain.
Thank you.
Okay. Any last question for Sophia? No. Well, then let's thank her again. Very nice talk. see you next seminar in Japan. Seminar in a couple of weeks. Okay, so we have the next seminar in a couple of weeks is about. Okay, well then. Keep tuned. We will announce it on time. At this time.
Thank you.